how weather works, the science behind phenomena, the eternal dance above. In the vast theatre of Earth's atmosphere, an eternal performance unfolds. Above every meadow and mountain, beyond every horizon where sky meets sea, the great machinery of weather turns in its endless cycles. This is the story of that machinery not told in the language of urgency or alarm, but whispered like wind through ancient trees, spoken in the rhythm of rainfall on quiet leaves. Weather is the planet breathing. Each storm system that crosses the continents, each gentle breeze that stirs the grass, each snowflake that forms in the crystalline heights, these are expressions of a profound dialogue between sun and earth, between ocean and sky, between the molecular and the magnificent. To understand weather is to glimpse the fundamental forces that have shaped life itself, that have carved valleys and filled seas, that have determined the rise and fall of civilizations with the patient inevitability of clouds gathering on a summer afternoon. Tonight, the journey leads through the architecture of atmosphere, into the birthplace of clouds, across the pathways of winds that girdle the globe. Here, in this quiet exploration, the violence of the storm becomes a ballet. The chaos of turbulence reveals its hidden order, and the simple act of morning dew forming on a spider's web connects to the vast engines of energy that power the planet's climate. Let consciousness drift like a high cirrus cloud, thin and peaceful, as the mechanisms of weather reveal themselves not as distant abstractions, but as intimate processes happening even now, in the air around this very moment, in the breath just taken, in the unseen currents flowing past in the darkness. Part 1. The architecture of atmosphere. The atmosphere wraps Earth like layers of gossamer veils, each with its own character, its own purpose in the grand design. Beginning at the surface where life dwells, the troposphere extends upward for roughly 10 kilometers, though this boundary shifts like a living thing lower at the poles where cold air compresses, higher at the equator where warmth causes expansion. This is the workshop of weather, containing nearly 90% of the atmosphere's total mass, all the water vapor that will ever become cloud or rain, all the dust and seeds around which droplets form. Within this lowest layer, temperature decreases with altitude in a steady gradient, dropping approximately 6.5 degrees Celsius for every kilometer climbed. This cooling is not arbitrary but fundamental, the result of decreasing pressure as molecules spread farther apart, their collisions becoming less frequent, their energy dissipating into the expanding space. At the top of the troposphere, temperatures reach -60 degrees Celsius, cold enough to freeze carbon dioxide, though that particular transformation remains the province of other worlds. Above the troposphere lies the stratosphere, extending to 50 kilometers overhead, where temperature surprisingly reverses its trend and begins to warm again. Here dwells the ozone layer, that molecular shield absorbing ultraviolet radiation, converting dangerous energy into heat. The stratosphere remains remarkably stable, its air stratified in orderly layers with little vertical mixing. Weather cannot penetrate this realm, except in the most violent circumstances. The overshooting tops of supercell thunderstorms occasionally punch through the boundary, carrying water vapor into regions where it forms strange, electric blue noctilucent clouds, visible only in deep twilight. The mesosphere continues upward to 85 kilometers, where temperatures plunge again to the coldest naturally occurring conditions on Earth, -90 degrees Celsius or colder. Here, the air has become so thin that concepts of temperature begin to blur. Molecules travel great distances between collisions. Meteors burn in this region, their incandescent trails marking the transformation of cosmic debris into light and heat and scattered atoms that will eventually drift down to Earth's surface over centuries. Beyond the mesosphere, The thermosphere extends to 600 kilometers or more, where solar radiation heats the few remaining molecules to temperatures that would read as thousands of degrees on a thermometer. Though a human exposed to this environment would freeze instantly, there are too few molecules to transfer that heat to anything substantial. This is the realm of the aurora, where charged particles from the sun collide with oxygen and nitrogen, exciting electrons that release photons as they return to ground state, painting the polar skies in curtains of green and red and violet. The exosphere, that final frontier before space, has no clear boundary. Molecules here follow ballistic trajectories, arcing through the void, some escaping Earth's gravitational embrace forever, others falling back to rejoin the envelope of gas that makes life possible. Hydrogen and helium, the lightest elements, predominate at these heights, their low mass allowing them to reach velocities that carry them beyond escape velocity when solar heating provides sufficient energy. Now, close your eyes and picture how all of this might look. Layer upon layer of invisible architecture, each zone with its own properties, its own role in the complex system that creates the weather experienced far below. See the troposphere churning with convection currents, the stratosphere floating in serene stability above, the mesosphere glowing with meteor trails, the thermosphere shimmering with aurora, and the exosphere gradually fading into the infinite black of space. This vertical structure sets the stage for everything that follows. Within these layers, particularly within that dense, dynamic troposphere, the engines of weather operate according to principles both simple and profound. Energy arrives from the sun, distributed unevenly across Earth's curved surface. This imbalance drives everything, every wind, every storm, every gentle morning mist rising from a pond. The atmosphere tempts constantly to equilibrate, to balance the hot and cold, the high pressure and low, yet perfect balance never arrives. The planet turns, the seasons change, and the atmosphere continues its eternal effort to find equilibrium in a system designed for perpetual motion. Consider the sheer mass of air overhead, approximately 5 quadrillion metric tons pressing down on Earth's surface, creating the pressure that allows liquid water to exist, that fills lungs with each breath, that provides the medium through which sound travels. Every square meter of surface experiences roughly 10 tons of atmospheric pressure, yet life has evolved within this invisible weight, bodies pressurized from within to match the pressure without, existing in perfect balance with the ocean of air above. If this gentle vision of the atmospheric layers soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo beneath the vast sky above. Part 2. The Birth of Clouds. In the realm where water transforms from invisible vapor to visible droplet, clouds are born through processes of elegant simplicity and fractal complexity. Every cloud that has ever formed, from the smallest wisp of morning fog to the towering anvil of a supercell thunderstorm, began with the same fundamental requirement: air must cool to its dew point, that precise temperature at which water vapor condenses into liquid. This cooling happens through various mechanisms, each producing distinct cloud types that paint the sky in endless variations. When warm air rises, it expands as atmospheric pressure decreases, and this expansion causes cooling without any heat being removed, an adiabatic process, thermodynamics manifesting in the vertical dimension. As a parcel of air ascends, it cools at the dry adiabatic rate of approximately 10 degrees Celsius per kilometer until reaching saturation. Once condensation begins, latent heat releases, warming the rising air and slowing the cooling rate to about 6 degrees per kilometer, the moist adiabatic rate. But condensation requires more than just cooling. Pure water vapor, even when supersaturated, resists forming droplets. The energy barrier for creating a new surface between liquid and gas proves too great for spontaneous droplet formation under normal atmospheric conditions. Enter the condensation nuclei, microscopic particles of dust, salt, pollen, volcanic ash, even bacteria, around which water molecules can gather. These particles, numbering in the millions per cubic meter of air, provide the scaffolding upon which clouds build themselves. Ocean spray contributes salt crystals that are particularly hygroscopic, attracting water molecules even before saturation occurs. Desert dust, carried on transcontinental winds, seeds clouds thousands of kilometers from its origin. Forest fires inject ash and organic particles that can alter precipitation patterns across entire regions. Even cosmic dust, the remnants of ancient supernovae, serves as condensation nuclei, connecting Earth's weather to stellar processes that occurred billions of years before the solar system formed. The process begins at the molecular level. Water molecules in vapor phase collide with a condensation nucleus. Some stick, held by hydrogen bonds. More molecules join, forming a thin film of water around the particle. As the droplet grows, surface tension creates a sphere, the shape that minimizes surface area for a given volume. These initial droplets measure mere micrometers across, so small that around 1,000,000 would fit on the head of a pin. Cloud droplets remain suspended because their full velocity is negligible compared to the upward motion of air in which they form. A typical cloud droplet falls at about 1 centimeter per second in still air, but even gentle updrafts exceed this speed. The droplets drift like dust motes in a sunbeam, carried by the slightest air current, colliding occasionally with other droplets, sometimes merging, sometimes bouncing apart. Growth from cloud droplet to raindrop requires a 1,000,000-fold increase in volume. This cannot happen through condensation alone. The process would take hours or days. Instead, precipitation forms through two primary mechanisms. In warm clouds, where temperatures remain above freezing throughout, the collision coalescence process dominates. Larger droplets fall faster than smaller ones, overtaking and collecting them. Some droplets grow large enough that their fall velocity exceeds the updraft speed, and they begin their descent toward Earth, growing through continued collection until emerging from the cloud base as rain. In cold clouds, where temperatures drop below freezing at higher altitudes, the Bergeron-Findeisen process operates. Ice crystals and supercooled water droplets coexist in an unstable arrangement. The saturation vapor pressure over ice is lower than over liquid water at the same temperature, causing water molecules to migrate from droplets to ice crystals. The ice crystals grow at the expense of the droplets, eventually becoming heavy enough to fall. As they descend through warmer air, they may melt into raindrops or remain frozen as snow, sleet, or hail, depending on the temperature profile through which they fall. The shapes of ice crystals reflect the temperature and humidity conditions of their formation. At -5 degrees Celsius, thin hexagonal plates develop. At -15 degrees, columns and needles predominate. Near -20 degrees, stellar dendrites create the classic six-armed snowflakes that grace holiday decorations. Each crystal's journey through varying conditions in the cloud creates unique patterns, no two identical, though all follow the same hexagonal symmetry dictated by the molecular structure of water ice. Now, close your eyes and picture how all of this might look. Billions of microscopic droplets, each one a perfect sphere, catching and bending light, together creating the white billows and grey masses that drift across the sky. See the ice crystals growing in the cold upper reaches, their geometric perfection emerging from molecular forces, their surfaces sublime laboratories where water transitions between phases. Clouds classified by altitude and structure reveal the atmospheric conditions of their formation. Low stratus clouds spread in uniform sheets when stable air is lifted gradually. Cumulus clouds bubble upward, where convection currents rise from heated surfaces. High cirrus clouds, composed entirely of ice crystals, trace the jet stream's path across the upper troposphere. Each type tells a story about temperature, humidity, stability, and the vertical motion of air masses. The morning fog that clings to valleys forms through radiational cooling on clear nights. Earth's surface loses heat to space, cooling the air in contact with it below the dew point. This fog pools in depressions like a liquid, flowing down hillsides, following stream valleys, creating landscapes of ethereal beauty as sunrise illuminates the mist from above. Orographic clouds develop where air flows up and over mountain ranges, cooling adiabatically as it rises, warming again as it descends the leeward side. Lenticular clouds, smooth and lens-shaped, hover motionless above peaks, while air streams through them at tremendous speed, standing waves in the atmosphere made visible by condensation at their crests. The study of clouds connects human observation to atmospheric physics, aesthetic appreciation to scientific understanding. Every cloud formation represents energy in transition, water cycling between Earth's reservoirs, heat moving from equator toward poles. In their endless variations, clouds demonstrate both the predictability of physical laws and the complexity that emerges from simple rules operating in a dynamic system. Part 3. Rivers of wind. Across the surface of Earth, invisible rivers of air flow in patterns both ancient and ever-changing. These winds, from the gentlest zephyr to the most powerful jet stream, arise from a single driving force, the uneven heating of the planet by the sun. This thermal imbalance, combined with Earth's rotation, creates the complex circulation patterns that distribute heat, moisture, and life itself across the globe. At the equator, intense solar radiation heats the surface, warming the air above, causing it to expand and rise. This rising air creates a zone of low pressure that draws in surface air from north and south. But the air does not flow directly north and south. Earth's rotation deflects moving objects, including air masses, to the right in the northern hemisphere and to the left in the southern hemisphere. This Coriolis effect, named for the French mathematician who described it, transforms what would be simple north-south circulation into the complex pattern of trade winds, westerlies, and polar easterlies that girdle the planet. The rising equatorial air, having shed its moisture in torrential tropical rains, flows poleward at high altitude. Around 30 degrees latitude, it has cooled sufficiently to sink, creating zones of high pressure, the subtropical ridges that coincide with many of Earth's great deserts. This descending air splits at the surface, some flowing back toward the equator as trade winds, some continuing poleward as the prevailing westerlies. This circulation cell, from equator to 30 degrees latitude, is called the Hadley cell, one of 3 major circulation cells in each hemisphere. Between 30 and 60 degrees latitude, the Ferrel cell operates through different mechanisms. Here, the circulation is driven not by direct thermal forcing but by the interaction between the Hadley cell to the south and the polar cell to the north. Like a gear turned by its neighbors, the Ferrel cell rotates in the opposite direction to the Hadley cell, creating the westerly winds that dominate the middle latitudes. These westerlies carried European explorers to the Americas, determined the movement of weather systems across the continents, and create the roaring 40s and furious 50s in the Southern Ocean, where no land masses impede their flow. At the poles, cold, dense air sinks and flows equatorward at the surface, creating the polar easterlies. Where this cold polar air meets the warmer air of the middle latitudes, the polar front forms a battleground between air masses that generates much of the dramatic weather in temperate regions. Along this front, waves develop, growing into the low-pressure systems that bring rain and snow to much of the populated world. High above the surface, at the altitude where commercial aircraft cruise, the jet streams flow like ribbons of concentrated energy. These narrow bands of high-speed wind, reaching velocities over 300 kilometers per hour, mark the boundaries between air masses of different temperatures. The polar jet stream, typically found between 40 and 60 degrees latitude, meanders like a river, its waves determining the paths of storms, the occurrence of heat waves and cold snaps, the distribution of precipitation across continents. The subtropical jet stream, flowing at higher altitudes near 30 degrees latitude, remains more stable, marking the poleward edge of the Hadley cell. During winter, when temperature contrasts intensify, these jet streams strengthen and shift equatorward. In summer, they weaken and retreat toward the poles. Their positions and strengths influence monsoons, guide hurricanes, and determine whether regions experience drought or flooding. Now, close your eyes and picture how all of this might look. Vast rivers of air flowing around the sphere of Earth, deflected by rotation, rising where heated, sinking where cooled, creating the trade winds that filled the sails of ancient mariners, the westerlies that carry weather systems across continents, the polar easterlies that bring Arctic cold southward. Local winds arise from geographic features and differential heating on smaller scales. Land heats more quickly than water during the day, creating sea breezes as cooler marine air flows inland to replace rising warm air over the land. At night, the pattern reverses: land cools more rapidly, and land breezes flow toward the ocean. These daily oscillations affect coastal climates worldwide, moderating temperatures, triggering afternoon thunderstorms, creating the conditions that make many coastal regions so hospitable to human settlement. Mountain and valley breezes operate on similar principles. During the day, mountain slopes heated by the sun warm the adjacent air, which rises along the slopes, creating valley breezes that flow upward. At night, the slopes cool through radiation, chilling the adjacent air, which then flows downslope as mountain breezes, pooling in valleys as cold air drainage that can create frost pockets and temperature inversions. The mistral of southern France, the chinook of the Rocky Mountains, the föhn of the Alps, these local winds gain their characteristics from topography. As air masses are forced over mountain ranges, they cool and lose moisture on the windward side, then warm and dry as they descend the leeward slopes. The Santa Ana winds of Southern California, heated by compression as they descend from the high desert, can raise temperatures by 20 degrees in a matter of hours and reduce humidity to single digits, creating extreme fire danger. If this gentle vision of global wind patterns soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo carried on the eternal winds. Monsoons represent wind patterns on the grandest scale, seasonal reversals driven by the differential heating of land and ocean. During summer, the Asian landmass heats intensely, creating a massive low-pressure zone that draws moist air from the Indian Ocean. This air rises over the heated land, cooling and releasing torrential rains that sustain agriculture for billions of people. In winter, the pattern reverses. The land cools, high pressure develops, and dry air flows from the continental interior toward the ocean. The trade winds, steady and reliable between the tropics, once determined the routes of commerce and exploration. Ships laden with spices, gold, and slaves followed these winds across the Atlantic and Pacific. The doldrums, where the trade winds of both hemispheres converge near the equator, could trap sailing vessels for weeks in windless heat. The horse latitudes, where the Hadley cells descend around 30 degrees latitude, earned their name from ships that allegedly threw horses overboard to conserve water when becalmed in these regions of light winds. Wind erosion sculpts landscapes over geological time. Sand dunes migrate across deserts, their shapes determined by prevailing wind patterns. Loess deposits, fine sediments carried by wind from glacial outwash plains, create some of Earth's most fertile soils. The harmattan carries Saharan dust to the Amazon rainforest, delivering essential nutrients that sustain the jungle's productivity. Asian dust reaches the Hawaiian Islands and beyond, connecting continents through atmospheric transport. The kinetic energy of wind represents one of humanity's oldest and newest power sources. From the first sailing vessels to modern wind turbines generating electricity for millions, humans have learned to harness these rivers of air. Yet for all our technological advancement, we remain subjects to the wind's power. Hurricanes still devastate, coastlines, tornadoes still level towns, and the gentle breeze that cools a summer evening still carries the same physical principles that drive the global circulation. Part 4. The Symphony of Storms. In the grand theatre of weather, storms perform as both creators and destroyers, sculpting landscapes, distributing water and energy, clearing the air of pollutants, while occasionally devastating everything in their path. Each storm, from the briefest summer thundershower to the most powerful hurricane, represents the atmosphere's attempt to restore balance, to move heat from where it accumulates to where it is needed, to release the potential energy stored in temperature gradients and moisture differences. The ordinary thunderstorm, the most common of tempests, begins with instability warm, moist air near the surface underlying cooler, drier air aloft. Given a trigger, perhaps heating from the sun, convergence along a front, or lifting by topography, this warm air rises. As it ascends and cools, water vapor condenses, releasing latent heat that makes the rising air more buoyant, accelerating its ascent. The cumulus cloud grows vertically, its top reaching toward the tropopause, where stable stratospheric air resists further rise, causing the cloud to spread horizontally in the characteristic anvil shape. Within this towering cumulonimbus, a complex circulation develops. The updraft, rising at speeds that can exceed 150 kilometers per hour in severe storms, carries water droplets upward where they freeze into ice crystals. These ice particles collide, generating electrical charge separation through mechanisms still not completely understood. Smaller ice crystals, carrying positive charge, rise to the cloud's upper regions. Larger ice particles, carrying negative charge, accumulate in the middle and lower portions. The charge separation intensifies until the electrical potential exceeds the atmosphere's insulating capacity. Lightning springs forth, a branching channel of ionized air reaching from cloud to ground or cloud to cloud, carrying currents of 30,000 amperes or more. The channel, mere centimeters wide, heats to 30,000 degrees Celsius 5 times hotter than the surface of the sun. This intense heating causes the air to expand explosively, creating the thunder that follows, sound waves radiating outward at 340 meters per second, their arrival delay revealing the lightning's distance. The downdraft develops as precipitation particles grow too heavy for the updraft to support. Falling rain and hail drag air downward, cooling it through evaporation. This descending air spreads outward at the surface as a gust front, lifting warm air ahead of it, potentially triggering new thunderstorm cells. The storm propagates, each generation seeding the next, until the supply of warm, moist air is exhausted or stability is restored. Supercell thunderstorms represent the aristocracy of convective storms, characterized by a rotating updraft called a mesocyclone. These storms, responsible for most significant tornadoes and giant hail, develop when wind shear changing wind speed or direction with height tilts and stretches the updraft, imparting rotation. The rotating updraft can persist for hours, continuously ingesting warm, moist air, while the downdraft and precipitation fall in a separate region, allowing the storm to maintain itself far longer than ordinary thunderstorms. Now, close your eyes and picture how all of this might look. The massive cloud building toward the stratosphere, its interior flickering with lightning, its base dark with falling rain, its top brilliant white in the sunlight, spreading outward in the jet stream's flow. See the rotation in the supercell, the entire storm system turning slowly like a cosmic wheel, drawing energy from the atmosphere's instability. Tornadoes, those violent vortices that inspire such primal fear, form when the mesocyclone's rotation tightens and extends downward. The conservation of angular momentum accelerates the spin as the radius decreases, like an ice skater pulling in their arms. Wind speeds in the most intense tornadoes exceed 400 kilometers per hour, sufficient to drive straw through telephone poles, to lift locomotives, to scour pavement from roads. Yet the tornado's path, typically less than 2 kilometers wide and 50 kilometers long, seems almost surgical in its precision, one house demolished, while its neighbor stands untouched. Hurricanes, typhoons, and cyclones, different names for the same phenomenon, represent heat engines on the grandest scale. Born over tropical oceans where water temperatures exceed 27 degrees Celsius, these storms begin as clusters of thunderstorms that organize around a common center. The Coriolis effect, negligible near the equator but increasing with latitude, provides the initial rotation. As the system strengthens, a positive feedback loop develops. Rising air creates low pressure at the surface, drawing in more warm, moist air, which rises and releases latent heat, further lowering the pressure. The hurricane's eye, that region of calm at the storm's center, forms when the rotation becomes so intense that centrifugal force prevents air from reaching the center. Here, air descends from above, warming and drying as it sinks, creating clear skies and light winds, while the eye wall, just kilometers away, rages with the storm's most violent winds and torrential rain. The spiral rain bands, extending hundreds of kilometers from the center, distribute precipitation across vast areas, sometimes delivering a year's worth of rain in a single day. These tropical cyclones serve as massive heat redistributors, moving energy from the tropical oceans toward the poles. A single hurricane releases energy equivalent to exploding a nuclear weapon every 20 minutes. Yet this violence serves the greater purpose of atmospheric balance. Without hurricanes and other tropical systems, the temperature gradient between equator and poles would intensify beyond what current life has adapted to endure. Winter storms operate through different mechanisms, driven by the collision of air masses rather than convection. Along the polar front, waves develop in the boundary between cold polar air and warmer tropical air. These waves amplify, creating areas of low pressure that intensify as they extract energy from the temperature contrast. The nor'wester brings warm air northward ahead of the system, while cold air plunges southward behind it, the frontal boundaries marked by clouds and precipitation. The transformation of rain to snow depends on the temperature profile through which precipitation falls. Sometimes a shallow layer of warm air aloft causes snow to melt and refreeze as sleet. Other times, the entire atmospheric column remains below freezing, allowing snow crystals to reach the surface intact. Freezing rain, perhaps winter's most dangerous phenomenon, occurs when rain becomes supercooled as it falls through cold air, freezing instantly upon contact with surfaces, coating everything in a glaze of ice that can snap power lines and topple trees. Blizzards combine heavy snow with strong winds, creating whiteout conditions where visibility approaches zero. The wind redistributes fallen snow, creating drifts that can bury buildings, while the combination of wind and cold produces wind chills that can freeze exposed flesh in minutes. These storms, like all weather extremes, remind humanity of nature's power, of our vulnerability to atmospheric forces despite all technological advancement. The study of storms reveals patterns within chaos, predictability within turbulence. Each storm follows physical laws, responds to measurable conditions, yet the complexity of interaction between variables means that precise prediction remains limited to days or hours. This boundary between order and chaos, between the deterministic and the probabilistic, defines much of atmospheric science. Part 5. The water's journey. Water moves through Earth's systems in an endless pilgrimage, changing phase and location, but never created or destroyed. The same molecules that fell as rain on ancient forests now flowing in rivers, frozen in glaciers, drifting as clouds, or resting in the deep ocean. This hydrological cycle, powered by solar energy and gravity, connects every part of the planet's surface, atmosphere, and subsurface in an intricate dance of evaporation, condensation, precipitation, and flow. From the ocean's surface, where 71% of Earth's area provides an essentially unlimited source, water molecules escape into the atmosphere. This evaporation requires energy 540 calories per gram absorbed from sunlight or from the surrounding water, cooling the ocean's surface. Each year, approximately 430,000 cubic kilometers of water evaporate from the oceans, while another 70,000 cubic kilometers rise from lakes, rivers, soil, and vegetation on land. The rate of evaporation depends on temperature, humidity, wind speed, and atmospheric pressure. Warm water evaporates faster than cold. Dry air accepts vapor more readily than humid air. Wind continuously removes vapor-laden air from above the water surface, maintaining the concentration gradient that drives continued evaporation. Lower atmospheric pressure, such as at high altitudes, allows water to evaporate at lower temperatures. Plants contribute to atmospheric moisture through transpiration, drawing water from soil through their roots, transporting it through vascular tissues, and releasing it through stomata in their leaves. A single large tree can transpire hundreds of liters per day during the growing season. The Amazon rainforest pumps approximately 20 billion tons of water into the atmosphere daily, creating its own weather patterns, generating clouds and rainfall that sustain the forest in a self-reinforcing cycle. Now, close your eyes and picture how all of this might look. Invisible columns of water vapor rising from every ocean, lake, and leaf, ascending into the atmosphere where they cool and condense, forming the clouds that will eventually return this water to Earth's surface, continuing the cycle that has operated for billions of years. Once aloft, water vapor becomes part of the atmospheric circulation, carried by winds sometimes thousands of kilometers from its source. The average residence time for a water molecule in the atmosphere is merely 9 days, though individual molecules may remain airborne for moments or months depending on their trajectory through the various atmospheric processes. Precipitation returns water to Earth's surface in forms determined by atmospheric conditions. Rain, the most common form, delivers approximately 100,000 cubic kilometers annually to land surfaces. Each raindrop results from millions of cloud droplets coalescing, growing until gravity overcomes air resistance. The largest raindrops measure about 6 millimeters across. Beyond this size, air resistance tears them apart. The smallest drops that reach the ground measure about 0.5 millimeter. Smaller droplets evaporate before completing their fall. Snow crystals tell stories of their formation and journey through temperature and humidity gradients in clouds. The delicate stellar dendrites that epitomize snowflakes form in a narrow temperature range around -15 degrees Celsius with high humidity. Columns and needles develop at slightly warmer temperatures. Plates and prisms emerge in colder conditions. As crystals fall through varying conditions, they may partially melt and refreeze, accumulate rime from collisions with supercooled droplets, or sublime directly from solid to vapor in dry air. If this gentle vision of the water cycle soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo like rain on distant leaves. Hail forms through a violent process of repeated ascent and descent within cumulonimbus clouds. Beginning as small ice pellets, hailstones are carried upward by powerful updrafts, accumulating layers of ice from collisions with supercooled water droplets. They fall when they grow too heavy for the updraft to support, only to be caught and lifted again if they encounter another updraft. Each journey through the cloud adds another layer of ice, creating the onion-like structure visible in cross-sections of large hailstones. The largest authenticated hailstone, recovered in South Dakota, measured 20 centimeters in diameter and weighed nearly a kilogram, requiring updraft speeds exceeding 160 kilometers per hour to remain suspended. Upon reaching Earth's surface, precipitation follows various paths. Some infiltrates into soil, percolating downward to recharge groundwater aquifers that may hold water for centuries or millennia. Some flows across the surface as runoff, gathering in rivulets that merge into streams, streams that combine into rivers, rivers that eventually return water to the ocean. Some collects in lakes and wetlands, temporary stopping points in water's journey. In cold regions, precipitation accumulates as snow and ice, locked in glaciers that store 69% of Earth's fresh water, releasing it slowly through melting and sublimation. The pathway water follows depends on numerous factors: soil permeability, vegetation cover, topography, antecedent moisture conditions. Clay soils, with their tiny pore spaces, resist infiltration, promoting runoff. Sandy soils accept water readily, but drain quickly. Vegetation intercepts precipitation, with forest canopies capturing 20 to 30% of rainfall, some evaporating directly back to the atmosphere, never reaching the ground. Root systems create channels that enhance infiltration, while plant transpiration removes soil moisture, creating storage capacity for future precipitation. Rivers integrate water from vast watersheds, their flow reflecting precipitation patterns across entire regions. The Amazon, Earth's mightiest river by volume, discharges 209,000 cubic meters per second into the Atlantic Ocean, more than the next 7 largest rivers combined. This flow represents the accumulated precipitation from a basin covering 40% of South America, demonstrating how the hydrological cycle connects distant locations through flowing water. Groundwater moves more slowly, flowing through pore spaces in soil and rock at rates ranging from meters per day in gravel to millimeters per year in clay. Aquifers, underground layers of water-bearing permeable rock or sediments, store vast quantities of water. The Ogallala Aquifer, beneath the North American Great Plains, contains approximately 3,000 cubic kilometers of water, accumulated over millions of years, now being extracted for irrigation faster than precipitation can recharge it. The ocean receives all water that flows from land, plus direct precipitation on its surface, minus evaporation. But the ocean is not uniform. Differences in temperature and salinity create density variations that drive thermohaline circulation, the global conveyor belt of deep ocean currents. Cold, salty water sinks in polar regions, flowing along the ocean floor toward the equator, while warm surface waters flow poleward to replace it. This circulation, operating on timescales of centuries, influences global climate patterns and redistributes heat around the planet. Water's residence times in different reservoirs vary enormously. Atmospheric water turns over every 9 days. Rivers replace their water in about 2 weeks. Large lakes may take decades to centuries. Groundwater residence times range from days to millions of years. Ocean mixing times average 3,000 years. Glacial ice can lock away water for hundreds of thousands of years. These different timescales create a complex temporal mosaic in the hydrological cycle, with rapid exchanges overlaying slower, deeper movements. The water cycle connects to other biogeochemical cycles through dissolution, transport, and deposition. Rainfall, slightly acidic from dissolved carbon dioxide, weathers rocks, releasing minerals that rivers carry to the ocean. Evaporation leaves these minerals behind, gradually increasing ocean salinity. Biological processes modify water chemistry. Photosynthesis releases oxygen, decomposition consumes it. Humans have altered the water cycle through dam construction, groundwater extraction, deforestation, and urbanization, changes whose full consequences continue to unfold. Part 6. Light's ethereal ballet. Light interacts with the atmosphere in ways that transform the sky into an ever-changing canvas of color and luminosity. These optical phenomena, from the simple blue of a clear day to the complex glory of a rainbow, arise from the fundamental properties of electromagnetic radiation encountering molecules, droplets, and crystals suspended in air. Each sunrise and sunset, each rainbow and halo, demonstrates physics principles that govern the behavior of light as it traverses the atmospheric medium. Sunlight arrives at Earth's atmosphere as white light, containing all visible wavelengths from violet at 400 nanometers to red at 700 nanometers. But this light does not pass through the atmosphere unchanged. Molecules of nitrogen and oxygen, much smaller than the wavelength of visible light, scatter short wavelengths more effectively than long wavelengths, a phenomenon called Rayleigh scattering, proportional to the inverse fourth power of wavelength. Blue light, with its shorter wavelength, scatters 16 times more readily than red light. This preferential scattering of blue light explains the sky's color. As sunlight enters the atmosphere, blue photons bounce off air molecules in all directions, filling the sky with diffuse blue light. The direct beam of sunlight, depleted of blue, appears slightly yellowed. Without an atmosphere, the sky would appear black, as it does to astronauts in space, with the sun a blazing white disk against the darkness. At sunrise and sunset, sunlight travels through a much longer path of atmosphere to reach an observer. This extended journey through air means more scattering occurs, removing not just blue but also green and yellow wavelengths. Only the longest wavelengths, oranges and reds, survive the passage relatively unscattered, painting the sky in warm hues. The exact colors depend on atmospheric conditions. Water vapor and dust enhance reds and oranges. Volcanic aerosols in the stratosphere can create spectacular crimson sunsets visible across entire continents. The green flash, a rare phenomenon visible in the final moment of sunset under perfect conditions, occurs because green light refracts slightly more than red, allowing it to remain visible for an instant after the red image of the sun has set. Clouds take on the colors of the light that illuminates them. At midday, they appear white or grey, depending on their thickness and the angle of illumination. But at sunrise and sunset, clouds become canvases for spectacular displays as they catch and reflect the warm light, while the ground below lies in shadow. Mammatus clouds, with their distinctive pouch-like protrusions, create especially dramatic scenes when lit from below by the setting sun, their bulbous forms glowing orange against a darkening sky. Rainbows manifest when sunlight encounters countless water droplets, each acting as a tiny prism. Light enters a droplet, reflects off the back surface, and exits, but not without being refracted, bent at each interface between air and water. Different wavelengths refract at slightly different angles, separating white light into its component colors. The primary rainbow appears at an angle of 42 degrees from the antisolar point, red on the outside, violet on the inside. Each observer sees their own personal rainbow, created by a unique set of droplets at the correct angle relative to their position. The secondary rainbow, fainter and with colors reversed, appears at 51 degrees from the antisolar point. It results from light that reflects twice within each droplet before exiting. Between the primary and secondary rainbows lies Alexander's dark band, a region where no rainbow light reaches the observer. Supernumerary rainbows, delicate pastel bands just inside the primary bow, arise from interference between light waves that have taken slightly different paths through the droplets. Now, close your eyes and picture how all of this might look. Light dancing through the atmosphere, scattering off molecules, refracting through droplets, creating the endless variety of optical effects that grace the sky. See the rays of sunlight made visible by mist, the halos around the moon on crystalline winter nights, the shimmering mirages rising from heated surfaces. Halos form through the interaction of light with ice crystals in high cirrus clouds. The 22-degree halo, most common of these phenomena, encircles the sun or moon when light refracts through hexagonal ice crystals randomly oriented in the sky. The crystals act as 60-degree prisms, bending light 22 degrees from its original path. The halo appears white or faintly colored, with red on the inside edge where refraction is least, blue on the outside where refraction is greatest. Sundogs, or parhelia, appear as bright spots on either side of the sun, often displaying rainbow colors. They form when plate-shaped ice crystals fall with their flat faces horizontal, refracting sunlight through their side faces. When the sun sits low on the horizon, sundogs appear at the same elevation, 22 degrees to either side. As the sun rises, they drift farther from it along the 22-degree halo, if one is present. The circumzenithal arc, sometimes called the upside-down rainbow, forms a brilliant circle of color high in the sky when sunlight refracts through horizontal plate crystals. This arc, often more vivid than any rainbow, appears only when the sun is lower than 32 degrees above the horizon. Light pillars, vertical columns of light extending above and below the sun or other bright lights, occur when ice crystals act as tiny mirrors, reflecting light toward the observer. Coronas, colored rings immediately surrounding the sun or moon, result from diffraction of light by water droplets or ice crystals in thin clouds. Unlike halos, which maintain a constant angular size, coronas vary in size inversely, with particle size smaller droplets create larger coronas. The aureole, a bright central disk, is surrounded by one or more colored rings, blue-green on the inside, red on the outside. When cloud particles are very uniform in size, the corona displays particularly vivid colors. Glories appear as colored rings around the shadow of an observer cast on clouds or fog, typically seen from aircraft or mountain peaks. This phenomenon involves a complex combination of diffraction, reflection, and interference as light travels around droplets and returns toward its source. The glory always centers on the antisolar point, directly opposite the sun from the observer. Each person sees the glory around their own shadow only, unable to see glories around the shadows of companions. Mirages arise from refraction in air layers of different densities, typically caused by temperature gradients near surfaces. The inferior mirage, common on hot roads, occurs when air near the surface is much warmer than air above. Light from the sky refracts upward as it passes through the density gradient, creating the illusion of water on the road. Superior mirages, where distant objects appear elevated or inverted, occur when cold air underlies warm air, bending light downward. These mirages can make ships appear to float above the horizon or create the Fata Morgana, complex mirages where distant coastlines transform into elaborate castles and cities. Crepuscular rays, those dramatic beams of sunlight that appear to radiate from a point in the sky, are simply shadows cast by clouds or mountains. The rays are actually parallel, but perspective makes them appear to diverge from the sun or converge at the antisolar point. When these rays appear to converge at the antisolar point, they are called anti-crepuscular rays, though they are the same phenomenon viewed in the opposite direction. The aurora borealis and aurora australis represent the atmosphere's interaction with charged particles from the solar wind. When these particles, mainly electrons and protons, encounter Earth's magnetic field, they are channeled toward the poles where they collide with atmospheric gases. Oxygen atoms emit green light at lower altitudes, red at higher altitudes. Nitrogen produces blue and purple hues. The aurora's curtains and rays trace the magnetic field lines, making visible the invisible architecture of Earth's magnetosphere. Noctilucent clouds, the highest clouds in Earth's atmosphere, form at altitudes around 80 kilometers in the mesosphere. Visible only during summer twilight at high latitudes, these clouds glow with an electric blue color when illuminated by sunlight from below the horizon. Composed of ice crystals condensed on meteoric dust, they mark the coldest place in Earth's atmosphere and may be becoming more common as atmospheric composition changes. The zodiacal light, a faint triangular glow visible along the ecliptic before dawn or after dusk, originates not in Earth's atmosphere, but from sunlight reflecting off interplanetary dust. This dust, remnants of comets and asteroid collisions, orbits the sun in the same plane as the planets. The Gegenschein, an even fainter glow directly opposite the sun, represents backscattered light from the same dust particles. Each of these phenomena demonstrates the atmosphere's role as an optical system of extraordinary complexity and beauty. Light's interaction with air, water, and ice creates an endless pageant of visual effects, each following precise physical laws, yet combining in ways that produce infinite variety. The careful observer can read in these displays information about atmospheric conditions, particle sizes, temperature gradients, and the presence of various atmospheric constituents. Part 7. The chemistry of air. The atmosphere is not merely a static mixture of gases, but a dynamic chemical reactor where molecules interact, transform, and cycle through complex pathways. These chemical processes, driven by solar radiation, biological activity, and human influence, determine air quality, influence climate, and sustain the conditions necessary for life on Earth's surface. Nitrogen comprises 78% of dry air, yet this abundant gas remains largely inert, its triple bond requiring enormous energy to break. Lightning provides one natural mechanism for nitrogen fixation. The electrical discharge is intense heat causing nitrogen and oxygen to combine into nitrogen oxides. These compounds dissolve in rainwater, forming nitric acid that delivers biologically available nitrogen to ecosystems. Certain bacteria have evolved the ability to fix nitrogen using specialized enzymes, converting atmospheric nitrogen into ammonia that plants can utilize, establishing the foundation of the nitrogen cycle that supports all life. Oxygen, 21% of the atmosphere, exists in a state far from chemical equilibrium, maintained only by continuous production through photosynthesis. Without life's intervention, atmospheric oxygen would gradually combine with reduced materials on Earth's surface, disappearing over geological time. The Great Oxidation Event, occurring approximately 2.5 billion years ago when cyanobacteria evolved oxygen-producing photosynthesis, transformed Earth's atmosphere from reducing to oxidizing, enabling the evolution of complex aerobic life. Now, close your eyes and picture how all of this might look. Invisible molecules dancing through the air, colliding billions of times per second, occasionally reacting to form new compounds, breaking apart under ultraviolet radiation, cycling through organisms and oceans and rocks in pathways that connect every part of Earth's surface to its atmosphere. Carbon dioxide, though comprising only 0.04% of the atmosphere, plays an outsized role in Earth's energy balance and biological processes. This trace gas absorbs infrared radiation emitted by Earth's surface, re-radiating it in all directions, warming the lower atmosphere in what we call the greenhouse effect. Plants consume carbon dioxide during photosynthesis, converting solar energy into chemical energy stored in carbohydrates. Respiration reverses this process, oxidizing organic matter and returning carbon dioxide to the atmosphere. The carbon cycle operates on multiple timescales. Rapid exchanges occur between atmosphere, vegetation, and surface ocean on scales of years to decades. Slower exchanges with deep ocean and soil carbon occur over centuries to millennia. The slowest cycle involves weathering of silicate rocks, which consumes carbon dioxide, and volcanic outgassing, which releases it, operating over millions of years and regulating Earth's climate on geological timescales. If this gentle vision of atmospheric chemistry soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo in the vast chemical symphony of air. Water vapor, varying from near 0 to 4% of the atmosphere, depending on temperature and location, acts as both the most important greenhouse gas and the primary vehicle for energy transport through latent heat. When water evaporates, it absorbs energy that travels with the vapor until condensation releases it, potentially thousands of kilometers from the source. This latent heat transport moves energy from ocean to land, from tropics to poles, from surface to upper troposphere, driving weather systems and moderating temperature extremes. Ozone exists in two distinct atmospheric regions, with very different implications for life. In the stratosphere, the ozone layer absorbs harmful ultraviolet radiation, protecting surface life from genetic damage. Ozone forms when ultraviolet light splits oxygen molecules into atoms that combine with other oxygen molecules. This process converts dangerous UV radiation into heat, warming the stratosphere and creating its stable temperature structure. Near the surface, ozone becomes a pollutant, damaging plant tissues and respiratory systems, forming through reactions between nitrogen oxides and volatile organic compounds in the presence of sunlight. Methane, produced by anaerobic bacteria in wetlands, rice paddies, and livestock digestive systems, as well as released from fossil fuel extraction and permafrost melting, acts as a potent greenhouse gas, trapping 28 times more heat per molecule than carbon dioxide over a century timescale. In the atmosphere, hydroxyl radicals oxidize methane through a complex series of reactions, eventually producing carbon dioxide and water. This oxidation process, occurring over approximately 9 years, limits methane's atmospheric accumulation, but also affects the atmosphere's oxidizing capacity. Sulfur compounds cycle through the atmosphere in various forms. Dimethyl sulfide, produced by marine phytoplankton, escapes from the ocean surface and oxidizes to form sulfate aerosols that serve as cloud condensation nuclei, potentially creating a negative feedback loop where warmer oceans produce more phytoplankton, more clouds, and thus cooling. Volcanic eruptions inject sulfur dioxide directly into the stratosphere, where it forms sulfate aerosols that reflect sunlight, cooling the surface for years following major eruptions. Aerosols, tiny particles suspended in air, influence climate through direct interaction with radiation and indirect effects on cloud formation. Black carbon from incomplete combustion absorbs sunlight, warming the atmosphere. Organic aerosols from vegetation and combustion can either warm or cool depending on their composition. Mineral dust from deserts affects radiation balance and delivers nutrients to ecosystems far from its source. Sea salt aerosols influence cloud properties over oceans. The complex mixture of aerosols in the atmosphere creates regional variations in their climate effects. The hydroxyl radical, though present at concentrations of only about 1 million molecules per cubic centimeter, acts as the atmosphere's primary cleansing agent. Formed when ozone photolysis produces excited oxygen atoms that react with water vapor, hydroxyl radicals oxidize most pollutants and trace gases, initiating reaction chains that ultimately remove these compounds from the atmosphere. The concentration of hydroxyl radicals determines the lifetime of many atmospheric constituents, earning it the title of atmospheric detergent. Photochemical reactions driven by solar radiation create and destroy numerous atmospheric compounds daily. In urban areas, the photochemical smog cycle begins with morning rush hour emissions of nitrogen oxides and hydrocarbons. Sunlight drives reactions that produce ozone, aldehydes, and other oxidants, reaching peak concentrations in afternoon. As the sun sets, photochemical production ceases, and ozone concentrations decline through reaction with nitric oxide and deposition to surfaces. The stratosphere hosts unique chemistry impossible in the denser, wetter troposphere. Chlorofluorocarbons, once widely used as refrigerants and propellants, reach the stratosphere where ultraviolet radiation breaks them down, releasing chlorine atoms. These chlorine atoms catalytically destroy ozone, with a single chlorine atom eliminating up to 100,000 ozone molecules before being removed from the stratosphere. The Antarctic ozone hole forms when unique conditions, polar stratospheric clouds, isolated air masses, and returning sunlight accelerate ozone destruction each spring. Biogeochemical cycles connect atmospheric chemistry to life processes. Photosynthesis and respiration exchange carbon dioxide and oxygen, nitrogen fixation and denitrification cycle, nitrogen between atmospheric and biological reservoirs, sulfur and phosphorus cycle through atmosphere, biosphere, hydrosphere, and lithosphere on various timescales. These cycles operated for billions of years before human influence, establishing the atmospheric composition that enabled civilization's development. Human activities have altered atmospheric chemistry on a global scale. Fossil fuel combustion releases ancient carbon to the atmosphere faster than natural processes can absorb it. Industrial agriculture fixes more nitrogen than all natural terrestrial processes combined. Deforestation reduces the biosphere's capacity to regulate atmospheric composition. These changes occur on timescales of decades, far faster than most natural variations, challenging Earth's systems to respond to rates of change unprecedented in human history. The atmosphere's chemical complexity emerges from the interaction of thousands of species through tens of thousands of reactions, influenced by temperature, pressure, radiation, and transport processes. Computer models attempting to simulate atmospheric chemistry must balance completeness with computational feasibility, including the most important reactions while parameterizing lesser processes. Despite decades of research, new chemical pathways continue to be discovered, revealing the atmosphere's seemingly inexhaustible complexity. Part 8. Climate's Deep Rhythms. Climate, distinct from weather's daily variations, encompasses the long-term patterns and averages that characterize Earth's atmospheric behavior over years, decades, centuries, and millennia. These patterns emerge from the complex interplay of solar radiation, atmospheric circulation, ocean currents, ice coverage, land configuration, and life itself, creating a system of extraordinary complexity that has varied dramatically through Earth's history, while maintaining conditions suitable for life for billions of years. The Sun provides essentially all energy driving Earth's climate system, delivering approximately 1,361 watts per square meter to the top of the atmosphere when perpendicular to the Sun's rays. Averaged over Earth's entire surface, accounting for the spherical shape and the fact that half the planet is always in darkness, this reduces to 340 watts per square meter. Of this incoming solar radiation, approximately 30% reflects back to space from clouds, ice, and land surfaces Earth's albedo. The remaining 70% is absorbed, warming the surface and atmosphere. Earth radiates energy back to space as infrared radiation, with the amount depending on temperature according to the Stefan-Boltzmann law. For the planet to maintain energy balance, incoming solar radiation must equal outgoing infrared radiation when averaged over time. This balance determines Earth's average temperature, but the greenhouse effect complicates this simple picture. Greenhouse gases absorb outgoing infrared radiation and re-emit it in all directions, including back toward the surface, requiring the surface to warm above what it would be for a planet without an atmosphere to achieve energy balance at the top of the atmosphere. The distribution of solar heating varies dramatically with latitude and season. The tropics receive intense, nearly perpendicular radiation year-round, while polar regions receive oblique rays that must traverse more atmosphere and spread over larger areas. During polar winter, no direct sunlight reaches the surface for months. This uneven heating drives atmospheric and oceanic circulation as the climate system attempts to transport heat from regions of surplus to regions of deficit, a process that never reaches equilibrium due to Earth's rotation and the continual variation in solar heating. Milankovitch cycles, named for the Serbian mathematician who calculated their effects, describe how variations in Earth's orbit and axial orientation affect the distribution of solar radiation over geological time. Eccentricity, the deviation of Earth's orbit from circular, varies on cycles of 100,000 and 400,000 years. Obliquity, the tilt of Earth's axis, varies between 22 and 24.5 degrees over 41,000 years. Precession, the wobble of Earth's axis, completes a cycle every 26,000 years. These cycles combine to alter the amount and distribution of solar radiation, pacing ice ages and interglacials. Now, close your eyes and picture how all of this might look. The Earth spinning through space, its axis tilted, tracing an elliptical path around the Sun, the subtle variations in its movement creating cycles of warmth and cold that span tens of thousands of years. Ice sheets advancing and retreating like a planetary heartbeat. Ocean currents transport enormous quantities of heat around the globe, moderating temperatures and influencing precipitation patterns. The Gulf Stream and its extension, the North Atlantic Drift, carry warm tropical water northward, warming Western Europe by up to 10 degrees Celsius compared to similar latitudes elsewhere. The Antarctic circumpolar current, flowing unimpeded around Antarctica, isolates the continent from warmer waters, maintaining its ice sheet. El Niño and La Niña events in the Pacific Ocean demonstrate how changes in ocean circulation can affect weather patterns globally, altering precipitation from Peru to Indonesia to Africa. The thermohaline circulation, driven by differences in water density from temperature and salinity variations, creates a global conveyor belt of deep ocean currents. In the North Atlantic, warm, salty water from the tropics cools and sinks, flowing southward at depth. This deep water eventually upwells in the Pacific and Indian Oceans, completing a circuit that takes approximately 1,000 years. Changes in this circulation, possibly triggered by freshwater influx from melting ice sheets, have been linked to abrupt climate changes in the geological record. Ice sheets and glaciers represent both products and drivers of climate. Their high albedo reflects solar radiation, cooling the surface. Once established, ice sheets create their own weather patterns, with cold, dense air flowing down from their summits. The weight of ice depresses Earth's crust, altering topography. As ice sheets grow, they lock away water, lowering sea level and exposing continental shelves, changing ocean circulation patterns. The Antarctic ice sheet contains enough water to raise global sea level by 58 meters if completely melted, while Greenland's ice sheet contains 7 meters of potential sea level rise. Feedback mechanisms amplify or dampen climate changes. Positive feedbacks include ice albedo feedback, where melting ice exposes darker surfaces that absorb more heat, causing more melting. Water vapor feedback operates as warming increases atmospheric water vapor capacity, and since water vapor is a greenhouse gas, this enhances warming. Negative feedbacks include increased infrared emission as temperatures rise, and enhanced rock weathering that consumes carbon dioxide as temperatures increase. The balance between positive and negative feedbacks determines climate sensitivity, how much warming results from a given forcing. Vegetation influences climate through multiple pathways. Forests have lower albedo than grasslands or deserts, absorbing more solar radiation. They also transpire enormous quantities of water, cooling the surface through evaporation while adding water vapor to the atmosphere. Trees emit volatile organic compounds that form aerosols affecting cloud formation. The expansion of forests during interglacials and their retreat during ice ages both responds to and influences climate change. The Amazon rainforest creates its own precipitation patterns, with moisture recycling multiple times as air masses traverse the continent. Past climates, reconstructed from geological evidence, reveal Earth's capacity for dramatic change. During the Cryogenian period, approximately 700 million years ago, ice sheets may have reached the equator in snowball Earth events. The Paleocene-Eocene thermal maximum, 56 million years ago, saw temperatures rise by 5 to 8 degrees Celsius globally, with subtropical conditions extending to the poles. The Mid-Pliocene, 3 million years ago, with carbon dioxide concentrations similar to today's, had temperatures 2 to 3 degrees warmer and sea levels 25 meters higher. Ice cores from Antarctica and Greenland provide detailed climate records extending back hundreds of thousands of years. Bubbles trapped in the ice preserve ancient atmosphere, revealing past concentrations of greenhouse gases. The ratio of oxygen isotopes in the ice indicates past temperatures. Dust layers reveal wind patterns and aridity. These records show that carbon dioxide and temperature have varied together, with glacial periods corresponding to carbon dioxide concentrations around 180 parts per million and interglacials around 280 parts per million. Tree rings, coral growth bands, lake sediments, and cave formations extend climate records beyond the reach of ice cores. Each archive has its strengths and limitations, but together they reveal climate variability on all timescales. The medieval warm period and Little Ice Age demonstrate regional climate variations over centuries. The Younger Dryas, a return to near glacial conditions 12,000 years ago that lasted over 1,000 years, shows that climate can change abruptly, shifting in decades or less. Climate models, mathematical representations of the climate system, integrate understanding of physical, chemical, and biological processes to simulate past and future climates. These models, run on supercomputers, divide the atmosphere, ocean, and land surface into millions of grid cells, calculating energy and mass transfers between cells at time steps of minutes. Despite their complexity, models must still parameterize processes occurring below the grid scale, introducing uncertainty. Nevertheless, models successfully reproduce observed climate features and changes, providing confidence in their projections. The carbon cycle regulates climate over geological time through the balance between volcanic outgassing of carbon dioxide and its removal through weathering and burial. When carbon dioxide levels rise, warming increases weathering rates, consuming more carbon dioxide and cooling the climate. This negative feedback has maintained Earth's temperature within bounds suitable for liquid water, despite the sun's luminosity increasing by 30% since Earth's formation. However, this thermostat operates over millions of years, too slowly to counteract rapid changes. Conclusion: the endless sky. As this journey through the architecture of weather draws toward its close, the atmosphere continues its eternal processes all around. Even now, in this very moment, water vapor rises from warm oceans, condensing into clouds that will deliver rain to distant continents. Winds flow in their ancient patterns, carrying seeds and spores, dust and dreams, connecting every corner of Earth in an invisible web of motion. Lightning flashes somewhere on the planet 44 times each second, maintaining the global electrical circuit. Ice crystals form in high clouds, bending moonlight into halos that few will pause to notice. The atmosphere asks nothing of conscious observation to continue its work. For 4.5 billion years, it has processed solar energy, distributed water, moderated temperatures, and enabled the chemistry of life. Long before humans evolved to wonder at rainbows or fear the hurricane's approach, weather systems crossed the planet in their stately processions. Long after the last human voice falls silent, the atmosphere will continue its patient work, its molecular engines running on principles that transcend any single species or epoch. Yet in this moment of awareness, As consciousness contemplates the vast machinery of weather, something profound occurs. The universe, through the emergence of observing minds, has developed the capacity to understand itself. The same physical laws that drive atmospheric circulation have given rise to brains capable of comprehending those laws. The carbon atoms that cycle through the atmosphere also form the neurons that perceive and ponder that cycling. We are not separate from the weather, but part of it, temporary arrangements of matter and energy that have gained the ability to recognize our place in the larger patterns. Sleep approaches now like a gentle weather front, thoughts condensing and settling like evening dew. The mind, that small weather system of electrical impulses and chemical reactions, prepares to enter its own quiet phase, its daily cycle of activity and rest that mirrors the planet's alternation between day and night. In sleep, consciousness retreats, but the brain continues its background processes, consolidating memories, repairing tissues, dreaming in patterns as complex and mysterious as any atmospheric phenomenon. Let awareness drift now, like a cloud releasing its burden of rain, becoming lighter, rising higher, dispersing into the vast peace of the atmospheric night. The knowledge of weather's workings settles into memory's deep sediments, where it will remain, ready to resurface when waking thoughts again turn skyward. The rhythms of breath align with the rhythms of wind, the circulation of blood with the circulation of oceans, the firing of neurons with the flash of distant lightning. Tomorrow the sun will rise again, heating Earth's surface, driving convection, powering the great engines of weather. Clouds will form and dissipate, rain will fall, winds will blow, and somewhere, someone will pause to observe these processes with wonder. But for now, in this gentle moment between waking and sleep, let the mind rest in the simple awareness that we exist within a living atmosphere, breathing its gases, drinking its water, sheltered beneath its protective embrace. The story of weather is ultimately the story of home, this small planet wrapped in its thin layer of gas, spinning through the cosmos, maintaining conditions that allow molecules to arrange themselves into forms that can contemplate their own existence. Every breath taken connects us to this story, to the Amazon rainforest producing oxygen, to the ocean's phytoplankton photosynthesizing in the sunlit surface waters, to the vast circulation patterns that distribute life's essential elements around the globe. As sleep's approach grows more insistent, like fog rolling in from the sea, let the last conscious thoughts be of gratitude for this atmospheric gift. The air that fills lungs with each breath has traveled vast distances, has been breathed by countless organisms, has participated in the endless transformations that maintain Earth's habitability. We are borrowing these molecules briefly, using them to power thoughts and dreams, before releasing them to continue their journey through the great cycles of the planet. Now consciousness fades like the last light of dusk, thoughts scattering like clouds dissipating in evening air. The weather continues its work in the darkness, outside storms building and declining, precipitation falling, winds flowing in their prescribed patterns. Inside, the small weather of human metabolism continues to oxygen converting to carbon dioxide, water vapor, exhaling with each breath, temperature regulated by the body's own thermostat. Rest now in the knowledge that you are held by the atmosphere, floating in an ocean of air at the bottom of Earth's gaseous envelope. Let sleep come like a gentle rain, washing away the day's accumulated thoughts, preparing consciousness for tomorrow's weather, whatever it may bring. The atmosphere will watch over this slumber, maintaining pressure and composition, filtering radiation, moderating temperature, continuing its billions-years-old vigil while dreams unfold in the darkness. And in those dreams, perhaps clouds will form from imagination's vapor, raining insights that will only be remembered as vague impressions upon waking. Perhaps winds of memory will carry fragments of this journey through weather's workings, weaving them into the strange narratives that consciousness creates when freed from waking logic's constraints. Or perhaps there will be only the deep, dreamless rest that restores both body and mind, as essential to life as the atmosphere itself. The endless sky continues its vigil, patient and eternal, as sleep finally arrives, as complete and enveloping as the atmosphere itself.